This is Obi-Wan Pez for Simplex Pachinko. We are going to be doing some math tonight, and now I've actually changed the stream title, so hooray. Hope you all are having a good week. Going to be hopping over here to our starting off with looking at some 2022 17. Now, unfortunately, at the moment, we're not able to use Microsoft Whiteboard except on the online version, and it's kind of laggy in terms of the interesting. It's also not showing the cursor at the moment, so that's fun. Okay, we'll see how this goes. Alright, so if anybody has any questions, feel free to drop them in chat, and I will get to it as soon as I can. Generally speaking, that's the way it works. There is no queue system at the moment, so maybe eventually we'll figure it out, but for now, just going to be working off of, you know, the patient system. Alright, so... Oh, that's weird. I've got I had two cursors there for a minute. That's... Oh, nice. That's gonna really mess with my head. Alright. Good job, Stream Elements. Alright, so what do we want to do? Man, I don't even know. So, let's see. Alright, so proposition, the sum of 3 cubes can express any integer. So this may not work for literally every integer, however, the interesting proposition is that we can add up any three cubes, and then we seem to be able to find any particular integer. So this number, or this problem was done out. Let's see. So this problem dates back to 1954 in Cambridge University, and mathematicians were curious as to whether or not this was going to be true. It seemed to work for as many numbers as they could find, but there were famously a couple of numbers that kind of eluded them. Wow. So for any particular value less than 100, the only numbers it did not work for were 33 and 42, and I think that might be equal to, it doesn't really matter. So the only numbers they didn't find it or as of 2019-ish. This was famously done on Numberphile. One of the mathematicians talked about it, and then within like a month, somebody found 33, and within another year or so, somebody else found 42. So now all numbers that are less than or equal to 100 can be expressed as the sum of three cubes. Not particularly nicely, but it works. And Blainlin, I see you there. Give me a second. So 1954 in Cambridge University, this was proposed, and then again in thanks to Numberphile, the problem was sent out to the wider community, and both of those numbers, 33 and 42, were shortly found thereafter. Again, within like a year or so. It doesn't particularly matter. So the sum of three cubes expressing any particular integer, we can also write this out algebraically as x cubed plus y cubed plus z cubed is equal to n cubed. So if we wanted to find like any particular n value, or find the sum of cubes that adds up to any particular n value, we could come up over here and say, all right, let's do x, y, z like this. Ew. have to do, I guess. So finding any particular x, y, z, and just for sake of right, without loss of generality, we could say that x is going to be less than y is going to be less than z, and those could be equal to each other. So it's just always going to be that the ones we pick, x is going to be the smallest, z is going to be the biggest, or they can be equal to each other in any combination. It just makes it easier because we don't have to do every possible combination. So for 1, for example, we can do 0, 0, 1. And then that's going to be the simplest arrangement of this. We don't have to do 1, 0, 0. We don't have to do 0, 1, 0. We just do 0, 0, 1 and just be done with it. Makes it easier. I mean, linear algebra is going to be harder. It's an application of all sorts of stuff. So, again, most of the time I do it in terms of matrix theory. Right, and there are also multiple combinations of other cubes that we could put in here, but all we need to do is just find one that works. So here, if x is 0, y is 1, and z is 1, then we get 2. For 3, we get 1 and 1 and 1, which is going to give us 3. For 0, we could just do 0, 0, 0. Again, you could have like -1, +1, and 0, but who cares? It's fine. As long as we can find at least one, we're good. Right, so sum of 3 cubes can express any integer in at least one way. So 4 and 5 I'm going to skip because they're slightly harder, and I don't remember what they are just off the top of my head, so it's meh. If anybody has them, let me know. It's probably not hard, I'm just missing it. So 6 could be, if we do 8, which is 2 cubed, so z will be 2, and both x and y are -1. Just going to make 2 cubed is 8 minus 1 minus 1 is going to be 6. 7, we could do 2, 0, -1. And for 8, we could do 0, 0, 2. For 9, again, we can do 0, 1, 2. And 10, we can do 1 and 1 and 2. All right, so then 11 is going to be, right, so like 8 and 3 we're not going to make. But you can do, if we move this up to 3, so that's going to be 27. And then 27 minus 11 is 16. So if we subtract off 2 8s, so -2 and -2. For 12, again, we have to just move it up by 1. Whoops. Huh. Did I mess that up? Oh, I didn't write 12, that's why. Alright, so that may actually require a bigger number. It's probably a nice application to do this in terms of linear algebra or something like that. So another way to start this is to say, okay, if we have n, what's n cubed going to be for any particular value? So going down our list, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we get 1,000 for 10 cubed. We get 729 for 9 cubed. We get 512 for 8 cubed. 7 cubed is 343. 6 cubed is 216. And no, this isn't in real time. I did this earlier. 5 cubed is 125, or in the case of the early ones here, I just know what they are. 64. 3 cubed is 27. 2 cubed is 8. 1 cubed is 1, and 0 cubed is 0. Then, of course, we have the negatives of those as well, but I'm not bothering to write those in because it's the exact same as this. It's symmetric, so it could just be the same as the other stuff up there. So this one is an interesting little item to just kind of do some like idle math. If you're ever just bored, need something to do, this is a good problem to think about for a little bit. So the idea here is we're just looking at the sum of cubes and trying out different numbers and seeing if we can come up with anything useful for, again, all of these particular numbers. So if we want things which are going to add up to 12, and again, we can only use 3 of them, right? We're not going to be able to get all of these individual numbers to simply, necessarily, add up to every single one of these. So 4, 5, and 12 I'm having some problems with just because it's not obvious to me right off the bat how to get one from the other. So let's see. Alright, so like 8 from 27 is 19, which then allows us to get 18 real quick. Or 11 like we did before. 27 twice from 64 is going to be 54 from 64 makes 10, so we've already got a 10. Don't actually need to do another one. Let's see. 27 from 64 is going to be a 37. And 8 from that, we can get a 29. So there are plenty of ways to get like certain numbers. You can eliminate those very simply and very easily. One of the other ways to do this is you just create a whole list of all of these numbers, and then you start checking them off as you find them. Which is, I think, what most of the mathematicians had done at Cambridge at the time. Keeping in mind they didn't have really any more sophisticated calculators than slide rules, which are nice, but meh. They help you do multiplication and division much more easily, and exponentiation much more easily, but addition, subtraction, not as much. May as well have an abacus for that. I suppose they also had the beginnings of computers at that point too. Right, so 264s minus 125 is going to be 3. 2 times 125 is going to be 250. Minus 216 is going to be 34. Right, 27 minus 8 minus 1 is, that's 18, right? Yeah. 2 8s and a 1 is 17. 2 8s and a 0 is 16. 2 8s minus 1 is going to be 15. So those are easy enough to figure out. But again, it becomes much more interesting when you start trying to figure out what some of these weirder numbers are that are in between. You start needing bigger numbers, and then you're subtracting larger numbers from them. As it turns out, so the one for 42, you're probably not going to like this. And again, this was highlighted on number file. They definitely did this when it came out. It was a negative 80 quadrillion, 538 trillion. American, by the way, sorry. 738 billion, 812 million, 75,000, 974, 974. Parentheses, cubed, plus 80 quadrillion, 435 trillion, 758 billion, 145 million, 817,515 cubed, plus 12 quadrillion, 602 trillion, 123 billion, 297 million, 335,000, 631 cubed. So all of that is equal to 42. They found their cubes, and it ended up working out. So that gets to be a bit much, and it is not super easy to find out or figure out what some of these are. And All right. For representations of 1 and 2, there are an infinite number of solutions due to the fact that, again, you could replace any of those zeros with a plus and minus of the same cube. And so it would always end up... you could always replace those two zeros with a positive and a negative of any cube you want. So... infinite number of solutions. And also 8 then, and I assume it's going to be probably all powers of all cubes, all perfect cubes. Can be scaled to obtain representations for any cube or any number that is twice a cube. Is that it? Weird. Yep. There we go. For positive n of 1,000 or less, and your x, y, and z values max out at 10 to the 14th, so 14 decimal places out, as of 2009, looks like. They had a finite number of, well, of course it's a finite number. So they had unknowns of 33, 42, 74, 114, 165, 390, 579, 627, 633, 732, 795, 906, 921, and 975. And it looks like 192, 375, and 600 allegedly still remain to this day. Andrew Booker discovered in 2019 that 33 has a solution, and also found that 795. Did I say that one? No. Okay. So 795 also had a similar solution. And yeah, September 2019. So actually, it was the same year. Andrew Booker and Andrew Sutherland computed the case of n equals 42 using the Charity engine. So this was a open source program that was much like Folding at Home or any of those other distributed computing systems. So they're able to show using the distributed computing system that 42 also worked. So all numbers less than 100, less than or equal to 100 work just fine for sum of cubes. Okay. That's why. Okay. So 4 and 5 were proven not to work. All right, so the reason that this works actually is kind of interesting. I did some of this earlier when I was talking about some research that one of my students was doing, and they were looking into the sum of squares, which again is slightly different, but it was the magic square problem, magic square of squares. So she was looking into when you have, a squared, b squared, c squared, d squared, e squared, f squared, g squared, h squared, I squared. When you do this, then she wanted to look at the individual. You can't even see that because I don't have a cursor. So she was looking at this right here and saying that, oh, well, if you end up finding out that like the sums of these numbers end up being some number mod 2, then it eliminates some possibilities in terms of no. The sums of these numbers can only be something mod 2, because the modulus of a square, is that it? Right, the square of any integer mod 2 has to follow a certain pattern, and the square of any integer mod 4 has to fit any pattern. And it works like this for any square mod a power of 2. So she was saying, let's do a magic square of squares, and then again, modulus of a power 2 ends up following a certain pattern, or a certain number of patterns. And so you can eliminate certain possibilities. Well, the same thing happens with sums of cubes. If you're looking at something mod 9, right, so for well, okay, 4 mod 9 is 4. And if we try, yeah, that's a thing. And if we take x cubed mod 9, then let's go back here. Actually, go the other way. That's not going to work. N cubed modulo 9 is going to be 0, and then 1, and then 8. Okay. So mod, again, modulo function is looking for what is the remainder of n cubed when you divide it by 9. So 27 is going to be 0. 64 when you divide it by 9 is going to be 63 plus 1. So modulo gets you a 1. 125 when you divide by 9, the closest number is I'm going to guess here 117. Right. 117 plus 8. 216 is evenly divisible. 342 is not, but Divide by 9 is going to be 27 with that left over is 8 with 1 left over is 72 plus 1. 512. Now, it's pretty obvious if you actually just do it, but I'm actually trying to reason through it. Yes, it's a cycle. So 512 divided by 9 ends up being 45 plus 6, and then 62. So normally you divide by 9, divide 63 by 9. In this case, you'd have to do 54, and then plus 8 gets you 52. And then 729 is evenly divisible because it's 9 cubed, and then 1 for 1,000 because 999. So this is a 3 cycle. Which goes 0, 1, 8. So then you look at this and you say, well, we've got 3 of them, right? 0 and 1 and 8. And if we were adding up 3, that can only ever be, or only ever have these moduli, then we're going to end up with like a times 0 plus b times 1 plus 8 times c. C times 8. Whoops. C times 8. So if we want some combination, some linear combination of A's, B's, and C's, given the factors of 0, 1, and 8, to then be equal to either 4 or 5, then we can figure this out, right? So if we look at these values, we go, okay, how can we get 3, for example? Well, 3 is just going to end up being 3 1s. 2 is going to be 2 1s and a 0. Right, so we've got some sort of linear combination of these things. All right, 6 is going to be, again, 1, 8, and 2 negative 1s. So negative 2 times 1. So let's do 12 here. Let's see. So this is going to be b plus 8c is equal to 12. So in what combination can we get these things? Mr. I love BBQ chicken? Yes. So on the order of 80 quadrillion, and then you cube it. Yeah. So that was discovered in 2019. Thanks to Numberphile exposing this, that it was an unsolved problem. And Andrews... well, they discovered it was an unsolved problem, or Numberphile highlighted that it was an unsolved problem, and Mr. Andrews, Booker, and Sutherland decided, you know what? we're going to undertake this. And they were working on number 42. Well, that's the thing, is that when something is unsolved, certain people like to stake their claim or try and work on it. Or, and here's the thing, right? It's not necessarily that, oh, well, it's unsolved, oh no. Sometimes people just want to check how fast their computer is and how good their programming skills are. So if they can figure something out like that, then why not try it? Why not throw it in there and see if over the weekend it can figure it out? I mean, obviously they didn't do this one by hand. True, but there are not necessarily ones that are like as easily figured out. So they figured, hey, let's see if we can get this. And again, they had a good algorithm for it, and in their cases, they used a distributed computing system. So it was something like, folding at home or whatever, but for math. So they were like, well, let's try it. So they just stuck it in there and let's see what happens. So it took them a little bit of time, which again, the distributed computing that they used was using background flops. So like stuff that the other people's computers were just going to waste anyway. I mean, hell, my computer's still running one right now that I'm thinking about it. Yep, totally. Yep, still running. I should probably pause that now that I'm streaming, but it's not like it's going to matter. You're probably not going to notice any difference, but 47 almonds. How's it going? And whereas, yes, I could argue, you are arguing that yes, there are better unsolved problems. It's one of those things like, we've got time. Again, those computer flops can go to something else, but like what? And do those people who stuck that algorithm in there have something else they want to solve? Do they have something that they find tenable, that they can reach? I mean, you all have seen some of the stuff that I've done. I'm going to have to, learn Python and possibly tensor calculus in order to figure this one out. But, for instance, I was trying to find out whether we could come up with a decent algorithm to figure... What the hell was I doing? I forgot the exact question that I was working on now. It's been so long since I've actually worked on it. Oh, man. Yep. Oh, n-dimensional. Right, it's my name, and Simplex, or the name of the channel here, and Simplex Pachinko, was to figure out, is there a way to figure out what the K1... Oh, that's what was eating the processing. Ah, no wonder. K4. It was the distributing computing system. Look at it. It's doing it in real time now. It's not rubber banding. So n choose K1, K through n dimensions. Do I want to do it that way? I think so. I'm having trouble remembering what the proper notation is. I think it's n choose all these others, possibly -1. How many do you choose? How many parameters do you choose? In a two-dimensional simplex, it's two things that you're choosing. Yeah, okay. So in this case, we have n factorial divided by k1 factorial, k2 factorial, multiplied by all factorials through kn factorial. So if I want to do this in n dimensions, I could be wrong about subscripts and stuff like that, but it doesn't really matter. So in terms of this, like you could kind of choose like what arg. So for this, you can choose. I'm circling it. You can't see it. There it is. Nope. Okay. Damn it. It was because I moved my mouse. Kind of slapped the desk. Anyway, in n dimensions, you're choosing like n parameters that you can use. So in two dimensions, you're... Yeah, that's not it. Whatever. Okay, so in two dimensions, you're doing n choose k. That's n factorial over k times usually r minus k. I think it's usually written as r minus k. N NCR. Yeah, never mind. It's just n minus k. And those are each individually factorial. So the way we're looking at this is we're saying that in two dimensions, we're doing a plus b to the n, and k is going to be which coefficient we want. And n is telling us which row. So if I want this as 2 choose 1, then we're taking our Yohui triangle here. You probably know it as the Pascal triangle. And we're saying this is a plus b to the 0. This one is a plus b to the first. This one is a plus b to the second. And we want to know what's going to happen when we have one of something that we're doing. Usually we're saying it's going to be when there's like 1a. It doesn't actually matter because it's symmetric, so as long as the a and b values themselves are symmetric, then we're fine. It's just which coefficient do we want. So in this particular case, this is 2. So we want the first location, where here the 1 is actually in the 0th position. So this is 1 a to the 0. Man. It's usually written the other way around. It doesn't matter again, but anyway. It's like a squared b to the 0 plus 2 a to the first b to the first plus 1 a to the 0 b squared. So it's in this way we're saying, okay, if we want to choose 1a from a selection of 2 variables that we get to pick, then we're going to end up with a coefficient of 2, which is saying that there are 2 different ways to get to that particular arrangement. So either if you're like drawing marbles out of a bag, for example, and you pull it out, you look at it, you record it, and then you replace it back in, and you shake it around and try again. So you got marbles that are labeled A and B, for example. So how many different arrangements do you have for pulling these marbles out of the bag? If you're doing 2 pulls, so that's what our 2 is. So 2 pulls, and you're going to get 1A. So that's what the 1 is on the bottom. So which row... I'm circling this again with my cursor. All right. My tablet pen does not like have the active cursor. I don't understand. Anyway, this is my mouse now. So which row is going to tell us, again, how many total things do we have? And which coefficient down at the bottom is going to tell us how many of this particular outcome do we want. Now, when you do something in more dimensions, it becomes much more complicated. And here I am talking about my research. Got on this topic from somewhere completely different. It's fine. If anybody wants any actual questions answered, please interrupt me. All right, so if we're doing this in like 4 dimensions, so what I mean by in 4 dimensions is what happens if we have an A marble, a B marble, a C marble, and a D marble. They're all put inside of a bag. They are equally likely to be chosen from the bag. So you could reach in, pull one out, you're just as likely to hit A, B, C, or D. Then in how many arrangements could we pull marbles out, given that we're going to pull, let's say, 3 marbles? So we want the number of combinations of, let's say, 1A, 3C, oh, 3 pulls, right, never mind. A. 1A, 2 Cs. Right, so how likely is that of 3 pulls? Well, this ends up being 3, choose, 1, 0, 2, 0. Because really, what this is up here, this is already implied. But in the old version, this wasn't just 2 choose 1. It was really 2 choose 1, 1. Because we want one of each of the variables that are there. One of each of the marbles. So a lot of times people don't put it there, but you really should. So, like, I didn't actually publish anything. I didn't really come to any conclusions that weren't already solved. So, whatever. And like I said, in order to do anything, like, further, I probably need to figure out tensor calculus and or some other stuff that ends up using the subscripts and superscripts stuff. So, let's see. Sorry. So like if we're doing this over here, again, this is symmetric to a lot of other stuff. So this is going to be the same as 3, choose 1, 2, 0, 0, or 3, choose 2, 1, 0, 0, or any other combination thereof, right? So trade those around any way you like. It's all the same. So generally speaking, we just say, without loss of generality, pick one. Try it out. Now, it becomes much more interesting when you start saying that you're more likely to pull a specific marble out of the bag. Like, here's the probability distribution of each of the individual marbles. We're not going to do that. We're just going to say that they're all equally likely, and so we're just going to pick an arrangement. So with 3 pulls, we want now 3, choose 1, 0, 2, 0. Okay, so this is going to be 3 factorial divided by 1 factorial, 0 factorial, 2 factorial, 0 factorial, which ends up being 3 factorial is 3 times 2 times 1, divided by 1 factorial is 1, 0 factorial is 1, 2 factorial is 2 times 1 is just 2, times 0 factorial is 1. So some people are like, well, why is 0 factorial equal to 1? That doesn't make any sense. It should be 0, right? Well, not quite. So here's the cheating way to do it. I'm going to pull from my hands a card from a deck. In how many ways can I pull an ace? The answer is 1, and here it is. I don't have any cards. Right? There is only one possible arrangement for 0 cards, and that is there aren't any. But that's important, is that there aren't any, and so that is an arrangement itself. And it's very important because, again, when you're doing stuff like this, when you have to multiply the number of different arrangements that you get for all of these things, you can't multiply by 0. You have to multiply by 1. There is also another representation of factorial, which is a continuous function, which also uses imaginary numbers. So it uses imaginary numbers in order to show you like what the value of a factorial is, no matter what the value is. So there is a value for like 6.3 factorial. There is also a value for like pi factorial. I don't like it, but there's a value. And it's also continuous between 3 factorial and 4 factorial. So pi factorial is between 3 factorial and 4 factorial, and it's a continuous function. There is a curve to it. And all values follow that curve. Again, it's a little weird, but it works. So in this arrangement, we've got our 2 up top and our 2 down bottom are going to divide out. And so we get 3 times 1 times 1 is just going to be 3 up top. And then 1 times 1 times 1 times 1 at the bottom is 1, which is just 3. So in 3 pulls, there are going to be 3 different ways in which we could get 1A and 2 C's. This isn't really all that surprising, right? It's just basically going to be a simplification of the two-dimensional version where you only have A's and C's. It's not really all that interesting, I guess. But what about stuff like, all right, we want oh, right, yes. thinking about in 3 poles, right? How would you get that's weird. Okay, in 3 poles, how would you get an A, a B, and a C? There should only be, I guess there are 3 different arrangements, right? ACB, ABC, and CBA. No, but that's going to be 6 because you could pull B's first. Huh. How'd I mess this up? Is it 3 factorial? That's the number of poles there are. Because on the bottom that'd be 1110. Okay. Now I'm having a problem with this. So we do 1A, oops, 1B, 1C, 0D. That'd be 3 factorial divided by, 6. Yeah, there we go. 1 times 1 times 1 times 1. Right, 0 factorial, 1 factorial, 1 factorial, 1 factorial is going to get us that. That's 6. 6 over 1. Okay, we're good now. Right, because again, we could do ABC, ACB, BAC, BCA, CAB, CBA. Right, so that's the easy way. Then you want to say, like, okay, in how many different ways can we get, like 8 poles? So if we did 8 poles, then how many different ways can we get, let's do 3, 1, 2, 2. Okay, so in this case we get 8 factorial divided by 3 factorial, 1 factorial, oops, 1 factorial, 2 factorial, 2 factorial. So this is going to be 8, 7, 6, 5, 4, 3, 2, 1, divided by 3, 2, 1, 1, 2, 1, and 2, 1. So for simplicity's sake, right, 2, 2, and 2 will knock out the 8. And then the 3 here can knock out the 3 there. Right, we could also do it from the 6, but it doesn't matter. So here we've got 7 times 6 times 5 times 4 times 2 is going to be 7 factorial divided by 3. 6 factorial is 720 times 7. 7 is going to be 49, 50, 50, 40. I used to know this. 50, 40 divided by 3. It's going to be 50, 51 is 17. So it's going to be 16. 2 left over is 8. So 1680. So 1,680 different combinations of choosing 3 A's, 1 B, 2 C's, and 2 D's. That seems like it might be high. I don't want to list them. But I mean, it's 8 polls, so that's a lot. So with 8 polls, you're talking like A, B, C, C, D, D. And then, right, move A along and just keep going. Move the second A along, move the third A along, and then keep cycling through, and then change all of the orders. So yeah, I think that makes sense. So this is saying that no matter where the first A is, it's the same as the second A and the same as the third A. So that's why we have this 3 factorial at the bottom. We don't care in what order those 3 A's go in, right? They are all going to be the same no matter what order they are in. So my intent was to figure out some sort of pattern that was going on with these things. Now, again, this is already done in terms of trying to figure out what this pattern is going to be, right? It's just n factorial for the number of poles divided by each of your individual parameters factorial. Yeah. So if it's n-dimensional, I shouldn't use n. Yeah. It's all good. So my actual research into this, which is, I think, original, question mark, is what's going to happen when you start looking at the rows of the triangle. Caught there for a second. Look at the sum of them. So going across in this particular triangle, we got 1, 2, here's 4, this is going to be 6, 8, oh my goodness, 10, 5 and 1 makes 6, 16, 32, 64, you name it. So this is going to be 2 to the n going down based on what row we're talking about. So for the nth row, the sum of them is all just going to be 2 to the n. Sorry. Right, yeah. So we call this the 0th row. And this one the first row. Because, you know. So again, my actual research into this was starting to say, all right, what happens if we're not just talking about this in terms of the 2-dimensional one? So there's 2 directions we can take this. Is that one of them can start talking about the 3-dimensional one. if we start taking this and using it as a pyramid, right, triangular base pyramid, or what is termed in mathematics as a 3 simplex, this is going to be a 2 simplex. Hey, it's coming together. This is going to be a 3 simplex. And if you want to talk about a 4 simplex, this is where things get a little weird. So you end up having a series of 3 simplices that are like embedded into each other. So here we have 1, 1, 1, 1. A 1 at each of the corners. One, 2, 1, 2, 1, 2, 1, 2, 1, 2, 2 back there as well. Alright, this gets really hard to draw, but basically you're gonna hopefully get the idea. This is 1, 1, 1, and 1, and along each of the edges we're now going to have 3s. And there's 1 space in the middle. Where all of the 2's from the above layer add up together. So it's going to be 1, 2, 3, 4, 5, 6 is going to be 12. 6 2's all combined together to get us 12 in the center of the 4 simplex at the third row. At this point, row just doesn't even make any sense. But we can also prove this by saying, yeah, well, if we do 1, 2, 3, 4 poles, and we want to know how many are going to be 1 of each. Right, this is going to be 4 factorial over, wait, hang on. That's wrong. Huh. So this is how to get 1, 1, 1, 1. Right, so I messed up. This is 3 poles. So there isn't a 12 here. Hang on. It's not possible, right? Because at this exact point, how did I mess up? So like these are A's, these are B's, these are C's, and these are D's, right? So starting from this location, well, starting from here, this is if we have no poles, then there's only 1 possible arrangement. There are none. If there's 1 pole, then we can have an A, a B, a C, or a D. That's it, just one. And then we move down a row, and we could have one arrangement in which we have A and A, right? Two A's. One arrangement for two B's, two C's, or two D's. Two arrangements for receiving an A and a B. So it's either A then B, then or B then A. So two. For receiving two A's and one B, then we have either two A's and one B, yeah, two A's then a B, A, B, A, or B then two A's. So three different arrangements to be able to get two A's and one B. This one over here is the reverse, two B's and one A. And then similarly for all the other combinations. So there's no possible way here to get one of everything, right? It's only three things. Oh, there is a center though. Yeah, okay. It's not one. That's what I messed up. Okay, so there's one here, there's one here, and there's one here. So this is yeah. This is a 6 and a 6 and a 6. So here, third row is going to show us so if we get three poles, and this is 1 1 1 0, 1 1 0 1, 1 0 1 1, or 0 1 1 1. So these four, whoops, sixes. These four sixes represent the four different arrangements to have three poles and only get one of each of the things. And then, obviously, there's going to be a fourth one that's just left out. So there's 6 different arrangements of each one of these. So again, A, B, and C. With no D's, you're going to have that same list that we had up there-ish, which was, again, ABC, ACB, etc. This is not super easy to, like, visualize this either. It gets pretty crazy. So naturally, if I want to go to the fourth row, now we're going to have some problems. Because this is, like, starting to really get big and nasty, and then we're going to have all sorts of three-dimensional bits which are on the inside of this three-dimensional bit, and this is a fourth row of this particular 4 simplex. Keep in mind, this is one thing. Right, you can't see that cursor. This is this is all one thing, right? This is one shape. Similar to how this is just one pyramid with all these individual separate layers, this here ends up being one 4-dimensional thing, which has a bunch of 3-dimensional layers inside of it. So I'd actually, yeah, I'd probably not use row and call it a layer. Oh, now we're starting with the laggy bits again. So this is going to have ones at all the corners again. And then it's going to have 4, 6, 4 along each of the sides. So 1, 4, 6, 4, 1 for all of these. Let's see, then this one is its own separate tetrahedron. How many different ways are there to do these things? So there's like a separate one here on the inside, attached to each of these. And then also one in the very center. Because there's the possibility of hitting exactly one of every one of these. And let's see, how many different ways are there to get that one? So to get A, then B, then C, then D, or every possible combination thereof, you're going to have 4 different things, and that's going to be 4 factorial divided by 1 factorial, 1 factorial, 1 factorial, and 1 factorial. So 4 factorial is 24. And then for the red ones here, this is going to be 4 factorial, 24, divided by 2, 1, 1, 1, so 12. So 4 12s. There's more than that, aren't there? Yeah, I'm having a hard time seeing it again. So normally I do this on like I actually have a 3-dimensional representation of this thing, just like as a pyramid of spheres, and so seeing them stacked like that, it's easier to see which ones contribute to which other ones. Actually, that's not true. It's which. Right, because these don't feed inward to the 6s, they feed downward to the next layer. Arc. One minute here. Alright. Sorcerer Juan, welcome on in. My name is Obi-Wan Pez. This is N Simplex Pachinko. Hopefully everyone's home for awesome math stuff. So I was looking at relaying some of the research that I was doing into n-dimensional simplices, and that is why my name, or the channel name, is what it is. So hopefully it is really awesome stuff that can inspire people. Yeah. Oh, let me introduce you to my little friend. Where'd he go? Oh no. Oh, there he is. The resemblance is kind of scary. Yeah, one of my friends found this, just sitting in a store somewhere, and was like, why is there a wall of him staring at me? So, yeah. Weird stuff, but we'll just go with that. So yeah, I was working with n-dimensional simplices here, and decided that it looked kind of like trademark here Plinko from The Price is Right, and then I was like, well, that's based on the old pachinko machines, which were gambling machines that, you know, it's basically pinball, but you're launching balls at a specific location. Usually you don't have flippers on the side, it's just like you launch them, and then they go through a little pachinko, clink, 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 and then eventually land somewhere. So that kind of looked like this for me, and then I was like, oh, I could create a 3-simplex version of this, and you could drop ball bearings through the top, and it would go through and then land in a little pan at the bottom, and you'd have a 3-dimensional representation of what we know in 2 dimensions as the normal curve. And so I commissioned our engineering department at my school to create a 3-dimensional representation of this, and so far they haven't gotten back to me, but I requested it pre-pandemic, so who knows. So it's in the fall of 2019 that I asked the guy to do it, so it was pretty much like right before we shut down. Yay. Newton's binomial. I don't think that I know that one in particular. So let's just real quick pull this up. Oh, is it literally just that? Oh, I see. Yeah, he was going off to infinity. Yeah, okay. Right, and using other numbers. Maclaurin series and all that. Okay. Yeah, it's been a really long time since I've done that, and yeah, no, I hadn't actually right, so that's not entirely what we're going for. So this stretches back all the way to, in terms of number theoretic triangles, the number theoretic triangle stretches all the way back to ancient China and to a mathematician named Liu Hui. Who is really the first one, at least that we know of, to work on doing the 2-dimensional triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. So he was the first one who came up with this stuff. And like I said, this is ancient. The first one to be able to come up with like the binomial theorem in terms of how it applies to algebra. I'm gonna have to remind myself on this one too. Al-Kharaji. Yep, I keep forgetting that guy's name. I'm gonna have to write it down. Oops. So Al-Kharaji was the first one in the Muslim world to discover the fact that this triangle here relates to algebra, in which our a plus b raised to the nth power has coefficients which are going to be represented by that triangle. And then Blaise Pascal came up with the idea that this all connects to binomial theorem in terms of statistics and probability. Right, and then Newton, hey, it's doing it again. It's the one who came up with the binomial theorem for calculus, where like n r and k are not always integers. So he could generalize it to anything. So this is also one of those things that we have to, yeah, no problem. This is also one of those things that like I keep having to remind both myself and my students, like this is not a super simple thing in order to like source exactly where it came from, because any of these could just be wrong also. It could have been someone lesser known in any of those times, but I mean, Newton probably was the one who generalized the binomial theorem to, you know, anything else. But for any of the other people, it could have been that they were the first ones to just publish it. You know, Al-Kharaji could have been the first one to like put it out there, much like, you know, Pythagoras was the first one to publish the Pythagorean theorem as a generalized formula, but it had been known in ancient Egypt for a long time because the people who were doing architecture like had knotted ropes that had Pythagorean triplets in like knotted in them, so that they would say, okay, all we need to do is take this thing that has, you know, a certain number of knots in it, pull it tight, make sure that we have a distance of 3, a distance of 4, and a distance of 5, and then, look at that, when we pull it tight, it makes a perfect right angle. Ta-da! So ancient Egypt, right? They knew exactly what they were doing with it. They didn't necessarily have like a formula for it, but they knew what they were doing. The application was there. That's what they cared about. It was kind of the same thing in ancient Rome too. So in terms of like the Romans, they didn't much care about the mathematics behind things as long as it worked, as long as it helped them with their conquest, as long as it was useful. That's all they cared about, which was really too bad for them. Yeah, I mean, I rediscovered um, what I was talking about here, the generalized triangle for n dimensions was going to be n choose k1, k2, dot 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 out to k sub m, right? Yeah, m. Right, the subscript is different than that number. Because you have m bins that you're selecting from, and you're choosing n of them. Sorry, you have yeah, you have n pulls from m bins, possible bins, and you want to know in how many ways I'm still circling. n pulls from m distinct bins. And like I didn't know what I was doing. I was just like, well, this is really cool because you've got, you know, up here, if we look at let's look at the 3 simplex, right? So the pyramidal structure of the whole thing is going to allow us to say, okay, if you have no poles, then there is one arrangement that's going to happen here. If you have one pole, then either you're choosing an A, a B, or a C. If you have 2 poles, then this is going to be the same as it always was for this is going to be the same as it was for any 2 of them. You're choosing either 0, 1, or 2 of any of these particular values. So essentially I marked these as a vector and said like we have the let's see, I chose this one as the nope that was the C vector. Oh, no, sorry. This is the 3 simplex. So if you choose these as your vectors, this is like your A vector, your B vector, and your C vector. And then coming down here, this is going to be kind of your N vector is going to tell you how many you're choosing. So in this particular case, you've got A, B, and C. So you're doing N right, number of poles. And then here you're doing like your A factorial, B factorial, C factorial. How many of each of them are you going to... Sorry, that's in the formula, not in this. Improper notation. So A, comma B, comma C. So I rediscovered that all of these individually are just how we're selecting these. So in this arrangement, how many are we going to go in each of these directions? So you could fall down using A to this 1 here, and then the B vector could allow you to fall to... I got this... Nah. The triangles are turned slightly. I messed this up. So fall along the A vector to get to here, fall along the B vector to get to there, and then fall along the C vector to get to the middle, the B vector again to get to this 3, the A vector again to get to that 3. So there's, you know, different numbers of ways to get to each of these individual things based on where you are in the triangle itself. In the 4 simplex, it becomes... Wait, I'm still pointing with my other cursor. Sorry. A vector gets you to here, and then the A vector again gets you to this 1, or the B vector gets you to this, or the C vector gets you then to A, then C, this 2 here. Right, because it could have been the other way around. The one that goes to C first, then to A, ends up getting you to the same place at the end. So there's 2 different ways to get to that particular location. So when I realized how I could get each of these individual numbers that were in these rows, or in the layers, and then generalized it to, oh, well, this is just going to be n choose ABC. I looked it up and it was like, oh, well, that's been known for 100, 200 years. Okay, cool. It was slightly disappointing. I had that big rush of discovery. I was like, yeah, this is awesome. And then, yeah, okay. It's been known for a long time. Whatever. So the thing that I'm trying to do that's going to hopefully be a little more unique is looking at the sums of these layers and figuring out what the pattern is that exists within these rows, or within the sums. So for the 2 simplex, this is well known, right? We have here, in the 2 simplex, we have 2 to the n is going to be the sum on any one row. Well, then, if, for instance, we want to know what the ratio is between any 2 rows, well, okay, in this one it's just 2 because you've got 2 to the n. So then the ratio between those rows is just 2. So that's less interesting. However, there was something else that occurred to me, which was, what if we don't just do this as the standard thing? What if we do this as a Fibonacci sequence? So we don't just add the previous numbers down to get this next number. We take the 2 previous and add them together to get the next one. So there's 2 different ways to go with this. One is that we look at this in terms of a Fibonacci type sum, which is going to say that, okay, we start with a 1. The next row is still going to be 1 and 1. And then the next row, the space here, is going to take the 2 rows above it that get to this particular position and add them up. Well, that's going to get us a 2. And no surprise here, if we go to the next one down here, that's going to get us 2 from here. It's going to be a 2 and a 1, so that's a 3. 1, 1, 2, 3. Okay. 5, 8, 13, etc. along the sides of this particular triangle. Again, not really surprising. It's going to be Fibonacci sequence. It was a Fibonacci addition, so okay, and then this is going to be separate from this thing. So 1, 1, 2, 3, 5, 8, 13, etc. So the the rows going down are eventually going to add up, or just get us the Fibonacci sequence. The ones in the middle are a little more interesting. So here we're going to add up the rows above them, the 2 rows above them. So here, this is going to be a 1 and a 1, and a 1 is going to be a 3. Okay, so then here we've got this one and that one. It's going to be symmetric again, and this is going to be the 2 rows above it that all contribute to this number. So for this one here, we've got a 2 and a 3 is 5, and then a 1 and a 1 is going to be 7. So 3, 7, 7, 3 is going to be the next one. So now we've got 3 numbers on the next row. Again, symmetric. So this number here is going to be a 3, 7 is 10, and a 2 and a 3 is 5, so that's 15 on both sides. And then the middle is going to be a 7, 7, 14, 16, 18, 21. Okay, so then Yep. And that's how I learned very late to do squares in my head super easily, right? So somebody asked me what's, 36 squared. I'm going to be doing, okay, well, that's going to be, you could also do, okay, that's 12 times 3. So square each of them, it's 144 times 9. All right, that's one way to go. Or you say, yep, 36. 36 squared is going to be, you got 30 squared, 900. 6 squared is 36, and then the combination of the two. So twice there is 540. So 900, 540, and 36. Yep. Yep, and then again here, this is going to be 20, 31, 31. And then the 2 in the middle here are equivalent. So 15 and 21 is 36. 7, 3, 7, 3. It's going to be 46, 56. So 56, 56 for the middles there. All right, and then this keeps going. So then I was like, all right, what about the sums of this stuff? Wow. So this is going to be 1. This is going to be 2. Going across here, this is now going to be 4 and 3 makes 7. Okay, so no longer powers of 2. And then here, this is going to be 20. This one here is going to be curses. 30, 51, 61. 112. And 62 is, man, I'm getting distracted here. 173, 189. So then what are the ratios of these things? Well, the ratios in this case are changing, right? Look at it. They're not the same number. So 189 over 61 is actually greater than 3. Okay, that's interesting. So how's this going to work? And then we can go through. That's probably wrong. In fact, 189 is probably wrong. 256 and multiply that by 2. Oops. Yeah, it's 190. Oh well. I should have realized there's no possible way, is there? Right, you'd have to have a middle number in order for it to be odd. So. At any rate, greater than 3. So we can find the ratios. And interestingly enough, the ratios, as we get further, start approaching a value. So it's going to approach a certain value. And then we could also do this for not just Fibonacci, but then what if we added the 3 previous rows to get the next row down? And 4 previous rows, and 5 previous rows, etc. Until when you get further, like, you know, all the way to the bottom here, the I don't know what you want to call it. The most complicated one is going to be this Infininacci, which I termed it, where you're adding all previous values going all the way up to get whatever the next term is, so that any one so 1, it's going to be 1 and 1 still. This is going to be 2 and 2 still, and here this is still 3. Next one down, though, you're adding up all the numbers. So 2 plus 1 plus 1 is 4. And then 4 plus 2 plus 1 plus 1 is 8. And then that added together is 16. So it ends up being that the outer edges are powers of 2. And then the inside stuff is really big. It starts getting really big really fast. So here, to get this particular place, we basically draw like a triangle from that particular point up. And then all of those numbers are going to be summed. So 2, 3, 1, 1, 1 ends up being 5, 6, 7, 8. So 4, 8, 8, 4. To get this particular term here, again, this is now going to be all of these added together. So it's going to be our 8 from all of this stuff up here added together, plus the 8 that's already here is going to be 16, plus this 4 here is going to be 20. I could be messing this up, but, you know, I think that's right. And again, here we're going to get another 20 on that side. Ew. 20. Right, and then we're going to get this middle number here, which is going to be summing all of this stuff, which is now going to be the 8 from all this top stuff, and then this 8 and this 8, so 24. So interestingly, the middle numbers don't differ all that much, at least at the beginning stages. And again, here, we're going to get the 20 that's here, the 20 from all this stuff, and then the 8. So that's going to be 48. And this position here, which is symmetric, is going to be found by right, so we got all of this stuff is going to be 20. Oops. Did I? Yeah. Did I mess that up? 24. 24 is going to come from this. So that's going to be 8 and 8 is 16. The 8 above it is 24, plus 2 is 26. Okay. So yeah, a little bit off. Then again, over here, this stuff is going to cut. It's going to take 26, which is all of this. 26 itself, which is 52. And then the 4 and the 4. 8 is 60, plus this 20 is going to be 80. Okay, so the middle numbers don't increase slowly. They're going to be big. Okay, so I'm going to stop there because this is getting way too out of hand, and I can just do this in Excel. So then I go with, all right, what's the sum going to be here? And then I would come across here and then try to find what the ratio is for all of this stuff. So the individual ratios, and then again, the total ratio, what all of this is starting to approach. So if you take it and you look at all of them, all the way through, going to this, what I've termed Fibonacci sequence, then it turns out that you do find that there is a ratio that underpins this. And I believe, I'm pretty sure, the ratio I found for this one is 1 plus square root of 2. That by itself was just, and again, it could be that it's a different one. It's not actually this one, it's like a, you know, Fibonacci or whatever, where you're doing like the 3 previous rows or something like that. But I thought that this was going to be all of them. It's been a long time. I have to go back over my Excel spreadsheets. They're at work. So here you look at this and say, okay, you know, all of this stuff ends up having a ratio of 1 plus the square root of 2. It was really weird. Like, I found what it was. Right, I had the ratio, I had the number in an Excel spreadsheet, and I was like, I've seen that number before, because it's, you know, 2.414 something or other, and I'm like, that looks so familiar. And I tried all sorts of little ways of like figuring out what it was going to be, how to get it, and then it just hit me. I was like, oh, that's what that number is. Right. So going over this, yeah, it does sometimes feel a little silly, where it's like, oh, well, maybe I shouldn't have been that excited. But no, you should be that excited. It was cool to have just made the discovery on our own, right? And it was the same thing I did. I knew it existed, so I shouldn't have been surprised there either. But I proved the in my pre-calculus class when I was, you know, 16, whatever. I ended up proving the change of base formula for logarithms, and I was just like, this is so awesome. And I, you know, showed it to my teacher, and she was like, huh? Do it on the board. I was like, So I presented it to the whole class, and you know, a few people appreciated it, and she was like, yeah, great. And then come the exam time for, you know, exponentials and logs, she had put that question on the exam, prove the change of base formula, and then I just snapped my head up and looked at her, and she was like, hmm. She was like, yeah, you know how to do that one. So I didn't, I mean, I'm pretty sure she just added it intentionally because I did this. So like, then we got into trig and everybody hated her. So, mathematician that inspires me. So like I don't think I have any one that like really stands out who's like, oh, I've got to absolutely, I love this person more than anybody else. I I think that at this point, like I've done minor research anyway into just the history of math, where I can appreciate the little stories that like everybody has, and trying to delve into, people who are obscure, people who aren't well known. I really love looking up stories of random people who, you know, didn't get their didn't get what they deserved probably in terms of historical treatment, and being like, "Hey, look at this person. Let's see how cool this is." So this is one of the things that I'm trying to do for this next semester especially, is to say like, let's find, actually, you know what I just found this book this last week. It was a book that one of my friends had as her it was in a class for like math history. So change is possible, put out by published with the authority of the Mathematical Association, American Mathematical Society, AMS, and stories of women and minorities in mathematics. So it's looking at like the history of math and how especially women and minorities have not gotten the credit that they deserve throughout history. And we end up seeing that it's always, it's always people who look kind of like this guy who end up getting a lot more credit for things. And I really want to go back and look up like ancient history and see what societies developed that we've forgotten. And it's really hard because, like, looking at the Rhine papyrus and stuff like that, there were a lot of discoveries that like the Babylonians knew about, the people who invented writing, right? They had like math problems on clay tablets that they gave to their students. Like, they had formal teaching in Babylonian times. This was 6,000 years ago. Well, 4,000 years ago, but stretching back to 6,000 years ago. They had like formal mathematics. So how far back could we actually go that we don't have this information for it? That there was non-permanent writing. Was there writing? Did they just write in the, sticks in the dirt for a while there? Probably. We can only prove that writing goes back about 6,000 years. What if we went back 12 and we just they didn't have the technology to permanently record it? How awesome would that be? I mean, we do see that there are like carvings and stuff like that, which are in, wood or bone or caves, and those go back 10, 20,000 years. But none of them have like quite the sophistication of the stuff we saw in the Babylonian era, which was like right, like horribly done, but nonetheless. No. get the point, but still. Hey, that's closer, anyway. Anyway. So, in ancient Babylon, right, they had a system of writing which was called cuneiform, which was done on clay tablets, and they had math problems that they set for their students. So one of them was awful. This is not what it looked like, but it's close enough. So anyway, so one of the questions that they did was something like, okay, if this ends up ooh, that's awful. Whatever. Okay, if are circumscribed by a square, you know, not all in that sense, but if the group of four circles are circumscribed by a square for totally identical. God, why? I hate Microsoft Whiteboard. You know, the app is not bad, but the problem is that I'm working on a Linux box right now, so I can't use it. Unless, of course, there is a Microsoft Whiteboard app for Linux that I overlooked, but... All right, so if a group of four identical circles are circumscribed by a square, what is the ratio to a... what is the area ratio to a square made by all four centers? So like this was a homework problem that was given to ancient Babylonian scribes. These are kids who were like between 8 and 15 basically. And they'd have to work out using mathematical reasoning how it was or what the ratio of the areas of the big to the small were going to be. So in this case, if we look at this, right, we can just assign a value for this. All right, so let's have it be 2 being the side length for the big ones. Oops. For the big. Is that a terrible idea? That's a terrible idea. That's all right. So let's make the radii. What? Nah, that's stupid. That's easy. Never mind. Hang on. There's a better question, not an easier question, a better question. I think it was the area of this thing. That's a better question. So we're saying, okay, what is the area of the big square divided by the area of the shape? So the way that they do this, and you know, I'm going to give this to my students. I don't know when, but at some point, just as like an interesting problem, not as something that they would need to do for, you know, calculus, because there's no calculus here. This is simple geometry. But if you notice, like each of these, right, and to appreciate the fact that this is like, we're all going to go about this slightly differently. So, right, each of these are 1. And so this makes a square. Area of the square with the pieces in it like this. It's going to be equal to 2 squared. So 4. And then, if you notice, the white space that's here is 4 quarter circles. So it adds up to 1 full circle with radius 1. So the area of that shape, this is super easy, but you know, area of this thing is going to be like 4 minus 1 circle is pi times radius is just 1, so 1 squared. So 4 minus pi. Right, and then the area of the whole figure, the whole thing here, this was 1, 2, 3, 4. So 4 squared is going to be 16. So that's 16 over 4 minus pi, which we could then approximate. So that's going to be a really interesting number. It's going to be fairly large. 18, 20, somewhere in there. I don't actually know. Yeah, it's not that big. 18.64. 6, 3, 9, 1, 6, 9, noise. 4, 6, it's bound to happen eventually, right? Like, practically any... Yes, I'm a child. That's fine. Practically any irrational number is eventually going to get us a combo in there. So anyway. I think I might give him that one on day 1. It's super easy. Right? It'll test some of their knowledge, they'll get some ideas going, allow them to try to submit their homework. Make sure they can do it online. I like it. All right. So it is now 11:35. I think we're going to wrap it up. If anybody has any questions, let me know. But apart from that, I think we're probably gonna call it a night. Hope everybody had some fun. We're going to raid over to who's on tonight. I know we got some friends. So, Juan, I did kind of cop out on that one. On your question about who's like my favorite mathematician. Again, you know, people I don't know about are really the ones that I want to look up. But, you know, there's a few that are like really inspirational in terms of they just really stuck with whatever they had and they were really insightful and didn't go with just what everybody else knew. I mean, like, Newton was a jackass, but he came up with a lot of cool stuff. Leibniz was he was a decent person, but like he was kind of run-of-the-mill. He just expanded upon the mathematics of his time and ended up inventing calculus on his own without Newton. Who else we got? Julie Robinson was somebody who like really worked hard at doing her research, and eventually over the course of about 30 years ended up almost solving but not quite solving Hilbert's 10th problem, I think it was, and then ended up getting contacted by, I don't remember his name, that's terrible. Hilbert's 10th problem. And Yuri Matyasevich. Oops. So Yuri Matyasevich ended up contacting Julia Robinson, and neither of them really spoke each other's language. They just tried best they could to communicate. And eventually they ended up collaborating on the end of Hilbert's 10th problem. Matyasevich, I think, essentially just solved it, but based on Julia Robinson's work. And the two of them were kind of this like symbol for the fact that, you know, Americans and Soviets can still cooperate despite our differences and despite the whole Iron Curtain thing that was going on. You know, Robinson went to Russia and Matyasevich came to America, and both of them did some collaboration and talking and, you know, mutual respect, all that good stuff. So it kind of became a symbol of fighting through the Cold War differences and coming together in the name of mathematics and science. So I really like, you know, their contribution together, even if it was, I guess, mostly political. It still ended up, you know, being this symbol of peace, working together for a greater cause. There's all sorts of other cool stuff, but like I said, Oh, I've been doing some research into Benjamin Banneker, who was a 1700s astronomer and mathematician who worked on creating an almanac back in 1700s. He himself was a freedman. I think his father was free and had been a slave. Yeah, I'm gonna need to remind myself of that one. It's been a little while since I did the research, unfortunately. So, Benjamin. There we go. Yeah, his father had been enslaved, and his mother had been, or his mother was free. So. Lived in Oella, Baltimore County, Maryland, and died at the age of 74 years old. 74 years. All right, so we're gonna go look at who's around. Let's see. We got, ooh, Jason Charles Miller's still on. Might have to raid in there. Yeah, we're gonna have to raid Jason Charles Miller. So JCM is a great mathematician. I love the guy. Or mathematician. Wow, no. Great musician. There we go. He would laugh at that. Come on. So Jason Charles Miller, great almost did it again. Great musician. I highly recommend picking up his music if anybody is thinking of getting some music. So we are going to go see him right now, and I hope to see you all on. Oh, I'm sorry, Mr. I Love BBQ Chicken. I didn't hydrate because apparently my chat froze again. Damn. I'm sorry. Well, we'll see you all later. Hopefully this Friday for some games, and next Tuesday for some math stuff. So, see you all later. This is Obi-Wan Pez for Simplex Pachinko. Have a good night.